In the last few classes, now what we learnt about Verilog is first we learnt about uh, gate level modeling, then we did data level modeling, and then we also saw how to take one module and put it into a bigger module, that which was known as instantiation. So today we will see some more new concepts. One is handling multi-bit data. Like till now we were only handling 1-bit data. Suppose I have a 4-bit data, or I can have a 16-bit data, right? How to handle those bits. Okay, and also something known as concatenation. Okay, so these are the two concepts which I am going to explain it today. Suppose this is an 4-bit adder. Okay, so now if you see here, I am adding A, which is a 4-bit data, to B, which is again a 4-bit data, right? So I write in a module. This is the name of the module. Input 30. Okay, what does input 30 means? Right, the MSB is at location 3 and LSB is at location 0. Okay, so you need to specify this is A now will be a 4-bit data, because here there you are declaring it as 30. So it is like if I declare it as 03, then A will be taken as a 4-bit data, but the MS will be taken as the as coming towards the right. Okay, so our normal convention is like this, right? 30. So we write MSB LSB with it as, so that option is also available to now swap the MSB. This 03 also you can write it, but then the number would look different, right? The MSB will come on the right side. Okay, so so generally we don't do that. We write 3030. Now if you declare the inputs like this, obviously the system will take A as an 4-bit number and 4-bit number, and a carry can be now again the sum will be again, like if you see here, sum will also be a 4-bit data, right? So it is 03, right? 03 means this is the like 0-bit, first bit, second bit, and S0, S1, S2, S3, like 4 bits, right? So sum will be sum you are again declaring as an output variable, 4-bit variable, and also there will be a carry, right? So carry normally, like we did in the last time, it's an single bit, so we declare it like this. Okay, so now concatenation means whenever you are putting in flower bracket, okay, that it will take this entire thing as an 1-bit as an single data. For example, if I am doing 4-bit addition, right, A and B, it is a 4-bit, this is an 4-bit, right? So that the net result will be 5-bit, right? Now if I write concatenation carry comma sum, that is carry is 1-bit, sum is 4-bit. So I'll this is a 5-bit total together. So A plus B, when I do, if I write a single command like this, automatically it will implement this entire circuit as it is here, right? So this is a very powerful tool, right? So this is data, we are not defining any gates and all, so we are just writing a data flow modeling, and we are using an concatenation here. So you don't have to, you just have to write an A plus B, sum and carry. So A plus B is A is 4-bit, B is 4-bit, sum is 4-bit, carry is 1-bit. So obviously once you do the addition, the expected result is 5-bit. So the MSB will come in automatically, will come in carry, and the lesser significant 4 bits will come in sum. So this is how we can write directly a program for a 4-bit adder. So I'll do this demonstration for you guys, but for the assignment parts, you have to do the binary coded decimal. Okay, now what is a binary coded decimal is, generally you have these displays, right? So each of these displays you will see here, it can have a 0 to 9 value only, right? So that is known as a binary coded. So each of, although for 9 you require 4-bit lines, but the net output is restricted to 0 to 9. Okay, so if it goes to 10, then it has to go to the next bit, right? So that is why these 4 bits will be restricted to only to 9. So how to do the binary addition is like you do 4 plus 5. BCD addition is so this is 4, this is 5, you add, you will get 9. Okay, this is fine. Okay, so there is no issue with this. Okay, expected result. Now if I do 4 plus 8, I do this is 4 in binary, I do this 8, I'll get 12 in binary, right? But this is not what I require for BCD output. I should get 1 and 2. Okay, so I will require two 4-bit outputs to drive like a 4-bit data, one 4-bit data to drive this first bit, second data, like if I am doing 8 plus 4, I should get 12, right? So 1 here, 2 here. So I should get 2 here. So this is 12 is not acceptable output BCD wise, right? So this is not. So I should get 12, right? So I should get output like this, 2, and then I should get 1 here. Okay. So this is what is expected out of an BCD addition. To how to generate that is whenever you add these things, and if you find this answer is more than 9, right? So maximum value which an BCD output can have is 0 to 9. So whenever it is more than 9, what you need to, greater than 9, you need to add 6. Okay, so if you do that, if you add 6, so automatically the answer what you get will be like this. Okay, so this is 1 and this is 2, 12, right? So what we are actually doing by adding 6 is from 10 to 15, whatever is the invalid states, we are skipping that. Okay, so that is the logic between of adding 6 out here. So when you add 6 here, so you will get the desired result. So whenever you do an BCD addition, if you detect that the answer is more than 10, what you need to do is you need to add 6 to it, so that you get the required BCD output. Okay, so now if you see there is one more condition. Suppose I do 9 plus 9. Okay, now if you see here 9 plus 9. So this is what I will get, right? And 1 plus 1 is 0, 0 plus 0 is 1, 0, 1 plus 1 0. So this is what, and this is again actually if I see BCD wise, this is 12, right? And 1 and 2, 12, but I require 18, right? So why this has happened is because this carry has been generated thinking that it has crossed 16. After crossing 16, it has gone there, whereas after 9 itself it should have crossed there. So you need to add another 6 here. So again this is also, if you add another 6 here, so you will get the desired result, right? Now it is now 1 and 8, 18, 9 plus 9, 18. So there are two different conditions. One, if a carry is generated, then you need to add 6, or the second condition, if there is if the now sum is greater than 9. So for you have to check for these two conditions. So if any of these conditions is matching, then you need to add 6. Okay, so this is how will be binary BCD adder will be implemented. You are adding 2 bits, right? So if there is a carry generated, okay, so if they you need to add 6, right? So from the OR gate, this is the final carry. Okay, there will be 2 4-bit adders, so this will be the final carry, and then to the result of these two sums, which again you are giving it here, you are adding 6. Okay, so if you see here, this is coming here, it is coming to the bit 2 and bit 1. So bit 0 and 3 are permanently 0. So whenever there is a 1 out here, if there is no carry, okay, 0 will come here. So this answer will come, like if you are adding 4 plus 4, you will get an answer 8 here. 8 will be available here. This will be 0 here. So you will add 0 to 8 and you will get the 4 plus 4, you will get 8. But if you are suppose you are adding 9 plus 9, 18. In that case, there will be 1 out here. Okay, so in this particular case, okay, this 1 carry output 1 will be there. So that 1 will come through here and it will add 6 here, right? Why is it adding 6 here? If you see, this 1 we have given it to B1 and B2, right? So this is, so it will. Now the second condition is if it is greater than 9, right? So then also you need to add 1. So if you see greater than 1 is 9 is these conditions, right? So as long as right, if this is 1, right, and any of these are 1, okay, this or this one and any of these one here, that means it is greater than 9. Okay, so this is 9, right? So for 10 it will be 1010, right? And for and for an 12 it will be like so. So for any it will be 1100. So if any of these bits are 1, still you need to add 6. So what I am doing is I am taking an AND of these two, AND of these two, and AND of these two also. So I am taking AND of these two. So if any of them again is 1 here, I put an OR gate and I again bring it the same. So in that condition also it will add an 1 and 1 out here, right? So if you see here, for all the two conditions, that is if there is a carry or if the sum is greater than 9, in both the conditions to the resultant another 6 will be added, so you will get the final answer out here. And this carry is of no meaning. This is the carry which is of interest. So this carry along with this will be the final BCD addition. So how to go about writing an BCD code for it is like first input is A and then input is B, then sum is 30, that is for this 4-bit adder, carry, right? Now we are calling this W1 wire 1 as an Z is equal to A plus B, right? Now so so this output, okay, wire 1. No, you need to declare this wire 1 is a single bit. So this is the A plus B information will be available in Z, okay. So you need to declare. I am just giving a hint, okay. So you need to declare this Z as an internal wire initially, right? Because this is internal. So you need to declare a wire, okay. So this is wire as 30. You are declaring it as. So assign W1 and Z as an A plus B. So Z will get the sum and wire 1 is the carry which is coming from here. So this is carry, right? Now wire 2 again, what is this wire 2? So these AND gates, right? So now you can see here this AND gate, right? So how do we specify this particular line? Okay, that will be called as Z3, okay, within square bracket. That means Z is a 4-bit data, Z3 means this Z3 and Z2. So you are defining this W2 as OR of these two gates, and these two gates is AND of Z3 and Z2 and Z1 and Z3. Okay, so Z1 and Z3. So these AND gates we are defining here and an OR gate here, right? And then you assign this as carry out here, right? So this you assign it carry, and then you are and now how to assign this value if you see here, okay. So once you assign W2, so the value of W2, W1, and then you get a carry is equal to, I have put a dash out here. So you need to complete the code out here, right? What is to be written here, right? So in fact, in carry will be just an OR of W2 and W1. Okay, so that will be the carry out here. You will get an carry out here, right? So now what about this? Okay, this is again another variable which you need to define, not variable, it is another wire, okay, W3. You need to define this as a wire, right? So wire 30, I am writing it as wire 3, right? So this wire needs to be defined. Again, that wire is I can define it as a C variable also here. C that is wire name of the wire is C, right? So now C is 1 bit 0, right? And 1 bit 0 means it is a 1-bit information where the first digit is 0, the next is carry, because you have already made this as a carry, right? This is carry, you have given a command now how to get carry, which is nothing but an OR of wire 1 and wire 2. So you already are getting carry, and carry here, this is 1 bit 0, that means this is 0. So what will be C will be 0, carry 0. That is 0 0, and here it will be carry which we have generated, right? And then again you use an adder expression. So some hints I have given here, but you need to design this BCD adder yourself. Okay, so you can refer to this slide and you get. Okay, the things which you need to remember out here is this we discuss. See, if you this you have defined as an single wire of 4-bit data, right? But you can do operations of single bits also, because this entire thing you have declared as Z. Now if I have to do between Z2 and Z2 and of these two wires, I can write like this, Z2 and Z2. Okay, so this is the thing which you need to remember. Another thing is this wire we have defined it as Z. Okay, 30. So the name of the wire is Z, 4-bit. This name of this 4-bit wire is C, right? And then you will add finally to get the BCD, you will add Z and C, right? Okay, so that you need to program it yourself. Okay, so this is some hints which I gave you how to go about doing the assignment, right? So I'm going to create a folder lab 4, and then I'm going to start a project. File, new project, right? Lab 4, and I'm going to lab 4. Next. The lab 4, I'm creating a new source, Verilog module. I am writing it as a 4-bit adder. No, I think I selected the wrong thing. Lab 4, new source, Verilog module. Okay. Four-bit adder, right? So now let me right. So this is an 4-bit adder. So what I can do is I can first go to the simulation, 4-bit adder. I can do an behavioral check. There is no issues with that. Then I do the simulation. Right now, if you see here, this is an on a force constant method. I can do the test. If I click out here, right, I can go to some on a force constant. So I can give either a binary, right, like force to a value 0 1 1 0, that is 3, right? Okay, and B force constant. So I don't have to always give binary. The entire flexibility is available with us. So let me give decimal, and 4 plus 3 I am doing, right? Okay, then I do an run. Right. So if you see here, this is 4 and this is 3, and the sum is actually 5, and the carry is 0. Right. So so this is how we can test, and also I can make an test bench also. So let me show you that also. So I go to the 4-bit adder, right click, new source, Verilog test fixture, test, next, finish. Right. So I get an test. And now the initial condition is A00. So after say 10 nanosecond, let me put one more condition out here, right? Okay, A is missing here. A equal to 1. If I write an A equal to say, let me give 4, it will take decimal 4. Okay, if I have to give it in binary, so the format will be 4 bit, right? And then I give 0 0, okay, 1 1. So this is 7, right? This is 4 and this is 3. So the answer should be 7 in this case, right? So so this is one test vector. So I can give many test vectors like that, right? So I do an let me write an dollar finish also. So now I do see the various ways of writing this. If I write it like this, it will take the decimal value. This is 4. If I write 4 inverted comma and then B, that means it's a 4-bit data. 4 plus 3 7. So I should get this. So if you see here again, right? This is the sum on top, it is 7 sum, so that is 7, carry is 0, and A is right, and 4, and this is 3, right? So you will find that is working fine. Now I can if you want to see how whether the carry is functioning fine, so I can copy till here and I can put here one more. And then let me add carry will be 4 plus 4 15. It has to go beyond 15, right? So this is only 3. So let me write 14 out here, right? And then do the simulation. So yeah, here if you see here a carry for the third condition, I have put a data which generates a carry here. So the carry is going from 0 to 1 out here, right? So if you see here, there is a carry which is being generated here because the net result was more than 15, right? So this is how. This is just a binary 4-bit addition, right? What you need to do is the BCD. So you need to first make this as a single module, and then call this as a 4-bit adder as a module in your BCD adder, and do the rest of the programming there. So some hints I have given. Rest of the things you need to do it yourself. Okay, thanks a lot for today.